Imagine digging up a piece of pottery, its surface worn by time. How can we figure out how old it is? Radiocarbon dating, a groundbreaking technique, gives us a window into the past. Developed in the 1940s, this method uses the decay of carbon-14, a radioactive form of carbon found in organic materials, to determine their age. From ancient scrolls to fossilized remains, radiocarbon dating has changed how we understand history. This essay will delve into the science behind this remarkable technique. We'll explore how carbon-14 is formed and its journey through the biosphere. Additionally, we'll examine the dating process, its accuracy, and factors that can affect the results. Finally, we'll analyze famous case studies, including the Dead Sea Scrolls and the Shroud of Turin, to illustrate the profound impact of radiocarbon dating on archaeology and history. This journey through time begins with understanding the fundamental component of this technique, carbon-14. Let's uncover the secrets of this radioactive isotope and its role in revealing the mysteries of the past. Far above the Earth, a cosmic dance is constantly unfolding. Cosmic rays, high-energy particles from outer space, collide with atoms in our atmosphere. This bombardment creates a cascade of secondary particles, including neutrons. These neutrons, in turn, interact with nitrogen atoms, the most abundant element in our atmosphere. This interaction leads to the formation of carbon-14, a radioactive isotope of carbon. Unlike the stable carbon-12, which makes up most of the carbon on Earth, carbon-14 is unstable and decays over time. This decay process is the cornerstone of radiocarbon dating. Once formed, carbon-14 quickly combines with oxygen to form carbon dioxide. This radioactive carbon dioxide then enters the Earth's biosphere through photosynthesis. Plants absorb it, and animals ingest it by consuming plants or other animals. Consequently, all living organisms assimilate carbon-14, making it a ubiquitous tracer in the web of life. The moment an organism dies, its interaction with the environment changes drastically. It no longer takes in carbon-14 from the atmosphere or through the food chain. The carbon-14 within its remains begins to decay at a predictable rate, like a clock set in motion millennia ago. This decay follows a process known as radioactive decay, where unstable atomic nuclei lose energy by emitting radiation. The rate of decay is measured in half-lives, which represent the time it takes for half of the initial amount of a radioactive isotope to decay. For carbon-14, the half-life is approximately 5,730 years. Scientists use this knowledge to determine the age of organic materials. By measuring the remaining amount of carbon-14 in a sample and comparing it to the initial level, they can calculate how long ago the organism died. This process, known as radiocarbon dating, relies on a fundamental assumption. The level of carbon-14 in the atmosphere has remained relatively constant over time. While fluctuations occur, scientists can calibrate these variations using tree rings and other dating methods, refining the accuracy of radiocarbon dating. The imperfect clock, unveiling the limitations of radiocarbon dating. While radiocarbon dating has revolutionized our understanding of the past, it's not without its limitations. Like any scientific method, it operates under certain assumptions and can be influenced by external factors. Understanding these limitations is crucial for accurately interpreting radiocarbon dates. One significant challenge is contamination. If a sample is contaminated with younger or older materials containing carbon, the resulting date will be skewed. For instance, a bone buried in soil with high organic content could absorb carbon from its surroundings, making it appear younger than its true age. Another factor is the reservoir effect. This occurs when organisms incorporate carbon from sources with different carbon-14 levels than the atmosphere. For example, marine organisms often exhibit older radiocarbon ages due to absorbing ancient carbon from deep ocean waters. Recognizing and accounting for these effects is essential for obtaining more accurate dates. Additionally, radiocarbon dating can only be used on organic materials. Artifacts made from inorganic substances like stone, metal, or ceramics cannot be directly dated using this method. However, scientists can often infer the age of these objects by analyzing associated organic materials, such as charcoal from a hearth or wooden beams from a structure. Deciphering the Dead Sea Scrolls, a triumph of radiocarbon dating. The discovery of the Dead Sea Scrolls in the late 1940s sent shockwaves through the world of biblical scholarship. These ancient manuscripts, hidden in caves near the Dead Sea, contained biblical texts and other writings dating back over 2,000 years. But their authenticity was met with skepticism. Radiocarbon dating played a pivotal role in confirming the antiquity of these precious documents. Samples of linen wrappings and parchment fragments were analyzed, revealing dates ranging from the 3rd century BCE to the 1st century CE. These results aligned perfectly with paleographic and linguistic analyses, solidifying the scroll's status as some of the oldest surviving biblical texts. The dating of the Dead Sea Scrolls is a testament to the power of radiocarbon dating in archaeology and history. It provided irrefutable evidence for the scroll's authenticity, offering invaluable insights into the development of Judaism and early Christianity. The scrolls, once shrouded in doubt, became a cornerstone of biblical scholarship, thanks in part to the precision of radiocarbon dating. The enigma of the Shroud of Turin. When carbon-14 dating sparks controversy. While radiocarbon dating has illuminated numerous historical mysteries, it has also been at the center of contentious debates. The Shroud of Turin, believed by some to be the burial cloth of Jesus, exemplifies how radiocarbon dating can ignite controversy and fuel ongoing disputes. In 1988, 3 independent laboratories conducted radiocarbon dating on samples taken from the shroud. The results were consistent, placing the shroud's creation between the 13th and 14th centuries CE. These findings contradicted the shroud's purported age and cast doubt on its authenticity as a relic from the time of Jesus. However, the controversy didn't end there. Critics questioned the validity of the samples, suggesting they might have been contaminated by repairs or handling over the centuries. Others argued that the dating method itself was flawed, citing possible variations in atmospheric carbon-14 levels. Despite these challenges, the 1988 radiocarbon dating results remain the most scientifically rigorous analysis of the shroud's age, fueling ongoing debate and speculation. Beyond the laboratory, the enduring legacy of radiocarbon dating. The impact of radiocarbon dating extends far beyond laboratory analyses and academic journals. It has revolutionized our understanding of the past, enabling us to reconstruct the timeline of human history, from early human settlements to the rise and fall of civilizations. It has also played a crucial role in addressing contemporary issues. By dating ice cores and sediment layers, scientists can reconstruct past climate patterns. This information is crucial for developing strategies to mitigate the impacts of global warming. As technology advances, so too does the precision of radiocarbon dating. New techniques allow for the analysis of smaller samples with greater accuracy. The continuous refinement of calibration curves enhances the reliability of radiocarbon dates. Radiocarbon dating remains an indispensable tool for unraveling the mysteries of the past. Its legacy shapes our understanding of history, archaeology, and the natural world. Radiocarbon dating will continue to be a cornerstone of scientific inquiry. If you enjoyed this video and want to learn more about fascinating topics like this, don't forget to subscribe to our channel. Thanks for watching.